All right. Hello, everyone. Welcome back to Comp 2160. We've got two classes left. We have two classes left. Yeah. Today's lecture should take us to the end of material for the course in terms of what I'm hoping for us to do. The material specifically that is the end marker for the course is when we talk about function pointers. That's the end of material for this course. I anticipate that we should be able to do everything that I want to do with that today. And then, time permitting, we'll move on and think about doing the Game Boy Advance stuff. What that means for tomorrow's class is that if we don't do the Game Boy Advance stuff today, we'll do it tomorrow. But the other part of tomorrow's class is basically going to be, let's talk about the exam, let's talk about the course, let's kind of do a step through of the learning outcomes that are being assessed in the course and the final exam, talk about the assignment. It's not going to be a hyper-structured class in the way that every other class has been so far. It's going to be just a little bit more, this is what we're thinking about right now. So with that, let's get straight to it. By the end of today's lecture, what I want you to be able to do is to use function pointers to parameterize behaviors. We're going to be taking a look at a few different parts of C today with the purpose of kind of trying to simulate OO. We're going to try to simulate OO with C using a couple of features that are called unions. That's the first one we're going to look at. And then the other one is going to be function pointers, where we're going to assign behavior to a structure. To start, I want to have you answer these questions. These are questions that I think you probably thought about in Comp 1020. And I've got a Mentimeter here, and I'd like you to share with me what you think about this. What even is a class, and what is inheritance? We're in a class right now. Yes, that is 100% true, yes. Class is a way of describing a specific thing. Inheritance leads to some sort of hierarchy of classes, so layers of abstraction. Those are good points, yeah. Like a group of things with like properties, not sure for inheritance, that's okay. Whatever you want it to be, I suppose. We can just define whatever words we want to be. We got the power to do stuff like that. Classes are collections of objects and their possible functions. Inheritance is passing traits of classes down. Yeah, I like that one. So I like these two where we've got a thing and where we've got these collections of stuff properties. Collection of related data, and inheritance is an extended or separate class that receives traits from the previous class. Class is a description of a thing, and inheritance specifies to have a subset of properties of that thing. Yes. Okay, these are all good. This is exactly what I'm thinking about when I'm thinking about classes and inheritance. Class is a collection of variables and functions that apply the class. Classes are groups of objects. They all refer to the same object. Inheritance takes similar portions of those classes, only the ones you need. Classes are objects. No idea of what inheritance are. That's okay. Inheritance is how much different objects in the code know about each other. This is coupling more than inheritance. Inheritance is that hierarchical relationship. We got parent class and we got subclass. The parent class has some behavior and some data. The child class extends that, and it inherits all of the behavior that the parent class has, and then we can kind of work on it. Class is a block of code. Inheritance is hereditary. When a mommy duck and daddy duck love each other very much. Yes, okay. Very good. Thank you all for sharing that. I'm going to switch over here. In C, classes are not part of the language. We can start to think about being able to simulate this. My question is, can we simulate this behavior, that behavior? And my answer to this is oh, you know what? Right now it's playing through my mind. It's playing. Okay. So it kind of goes like this. Let me build it. Yep. Yes. So we can sort of simulate this behavior. We can sort of simulate this behavior. We're going to need a couple of things to help us be able to accomplish simulating this kind of behavior. The first tool that we need to help us with this is called a union. This photo is of downtown Winnipeg in 1920, I think, 1920. This is the Winnipeg General Strike. This is a thing that happened in Winnipeg 100 years ago where the city basically shut down, kind of as a result of the Spanish flu and the war and all sorts of different things that were going on. And it's a really famous Winnipeg thing. So if you're bored after this course is over and you haven't had enough of playing my terrible game and C development, maybe check out something about the Winnipeg General Strike. If you've ever been downtown to the Pantages Playhouse, I think that's the place. There's a sculpture out in front of it where there's something that kind of looks like a streetcar that's like toppled and kind of embedded in the concrete. And that is an homage to this event because at some point there was a streetcar that got tipped over during the strike. It's a Winnipeg thing. We're going to be looking at a union as a type in C. This is a tool that we can use to simulate polymorphism. This is not the purpose of union, but we're going to use it to do this. We can use this tool to simulate polymorphism. The way that it looks when we type it out is that it looks a lot like a structure. We declare a name. So here I've got a union that has name thing. I've got properties inside of it. We have to put the semicolon after it, just like we do with structures. And we can do this type def on unions in the same way that we can with structures. The main difference between a structure and a union is that we can only really use one of these properties at a time. What I mean by that specifically is that each of these entries in the union are things that this can possibly be. It doesn't contain both of these things. It contains enough space for one of them, one or the other. The size of a union is the size of its widest type. So a double, for example, is something like 8 bytes, and an integer is 4 bytes. The size of a structure, let me go to this slide right here. The size of a structure is going to be the sum of the size of this double and the size of this integer. So for what we're thinking about, let's say that this is 8 bytes and this is 4 bytes. The size of this structure would be 12 total bytes. It has a property x and it has a property y, and we can use each of these in the structure. A union has the size of the widest type that's in it, and we should use one or the other of the properties that are inside of it. So if this is 8 bytes and this is 4 bytes, the size of this union is 8 bytes. It's as big as the widest type. Both of these properties will occupy the same physical space when we're thinking about a union structure like this. We can use this to try and simulate polymorphism. Polymorphism is this idea where we've got a parent class and then subclasses. And when we call a method, at least in Java, when we call a method on the subclass or an instance of the superclass type, it will figure out which method to call based on that type hierarchy that we have, that class hierarchy. We can kind of simulate polymorphism awkwardly with unions. And what I want to do here is I want to start implementing some code in a file that's called shapes.c that will try to demonstrate this. So I'm going to pop over to my terminal here, and I invite you to type along with me if you want. I'm going to copy my template into this directory to a file that's called shapes.c. And what I want to start doing here is I want to start implementing something that uses a union to represent different possible kinds of values. I'm going to implement a series of shapes. So I'm going to first start by declaring the different types that I'm going to use. The shapes that I'm going to have are really just going to have dimensions in them and nothing else. So I'm going to start with a struct rectangle. My rectangle structure is going to have, I'm going to use the types that we were using last class. So I'm going to include std_int.h. My rectangle type is going to have 8 bits for a width, and it's going to have 8 bits for height. I'm going to declare a triangle type. And my triangle type is going to have an 8-bit value for base and an 8-bit value for height. These are all unsigned because in terms of shapes, it doesn't make a lot of sense for us to have negative dimensions for a shape. The other one I'm going to have here is a circle. And a circle has exactly one property that I care about, which is the radius of the circle. In my main code, I can create instances of these structures, but I'm going to start doing something like what we did for some other types. I'm going to declare a function for each of these that's like the constructor function for each of these different types. So I'm going to start by making rectangle, make rectangle. And it's going to take as input a width and a height. This function is going to create an instance of that struct. And I'm going to use notation that we haven't seen before to do this. I'm going to initialize the struct in place. So what I've shown before in class is this notation where we set everything to 0 in a structure. But we can also use a property type notation to initialize things. So I'm going to say dot width is equal to width, and dot height is equal to height. This is just a nice little kind of shortcut for me to be able to initialize these things. Yeah. Why did we have to wait? This is a fairly new feature in C. Yes, yeah. It's not like 1 week old, to be fair, to be clear, but it's not something that you can rely on being in every C compiler. Yeah. So I'm going to make my rectangle, and I'm going to return my rectangle. I'm going to do something similar for my circle shape. And I'm going to return my circle. Remember that we're able to return stack allocated structures, and it will just go through the process of copying everything for us. The last one I'm going to make here is for my triangle, and it looks pretty much the same as what the rectangle one looks like. So triangle. I've got to change these declarations, sorry, to be struct rectangle. and struct circle. And then struct triangle, make triangle, base and height. All right. So I've got 3 types. I've got 3 constructor functions that I can use to initialize those types. And if I go down to my main function, I can create instances of those. So I can say struct triangle. Triangle is equal to make triangle with a base of 10 and a height of 50. Something like that. This is the same state that we were in 5 minutes ago. What I want to be able to do with this is I want to be able to create a type where I can assign any of those 3 types to it. So I want to basically have this structure, a shape superclass, and triangle is a subclass of that. A shape superclass and circle is a subclass of that. A shape superclass and rectangle is a subclass of that. And I want to be able to assign to this shape type any of those 3 types. I want to be able to accomplish the same thing here as I can in something like Java. So what I'm going to do to accomplish that is I'm going to add a new type to this using union. I'm going to go up to the top of this. And just beneath these 3 structure definitions, I'm going to add a new type that's called union dimensions. All shapes that we're going to have will have some kind of dimensions. I'm going to make an instance of a new structure that's called shape. I'm going to do this all in one line, type def struct shape. All shapes in this system have dimensions. Our shape structure consists of a union of type dimensions. And in this union, what we're going to put is each of the 3 structure types that we've got. So I'm going to pop these in, struct rectangle rect. Struct triangle, triangle, struct circle, circle. This is a union, so it's going to be able to have enough space for whatever the biggest thing is in here. These 2 are the ones that have the most amount of space. They both each have 16 bits worth of data to store in them. And the radius here that's in circle is just 8 bits. So the size of this dimension is going to be 16 total bits. And when we're using this structure, this union, we're going to have to refer to the one that we actually want to use here. So I've got my shape structure. I've got my union that contains each of the different shapes that I've got. And what I'm going to do is I'm going to amend the make functions that I've got. I want those to return an instance of shape as opposed to returning an instance of each of the different types that we're currently returning. So what I want to accomplish is make rectangle should not return a struct rectangle anymore. This should return an instance of the shape type. The way that I'm going to do that is I'm going to declare an instance of a shape inside of this function. So I'm going to say shape s is equal to, I'm going to use this notation that we've got here. And in here, I'm going to say that the dimensions, and now I'm going to have to set properties inside the union itself. So shape S shape here is the structure that I've got. Dimensions here is the reference to this union. And to access properties or to use properties of the union, I use that same dot notation. So here I'm going to say dimensions dot, and I'm trying to make a rectangle, so I'm going to say rectangle. Dimensions dot rectangle dot width. Dimensions dot rectangle dot, sorry, I'm just actually going to say this, is equal to rect. So I can set it, that rectangle reference, to be the one that I just declared above here. And then what I'm going to do at the end of this function is I'm going to return the shape S. So on line 42 to 44, I'm creating an instance of this shape structure here. I'm accessing the property, the one property that the shape has, which is dimensions. Dimensions itself is a union. The union, I can access individual things that are inside of that union by their name, so rectangle, and I can assign to them the value that I want to assign here. I'm going to go down to triangle, and I'm going to make the same changes. I'm going to say that this returns a shape. I'm going to declare an instance of shape inside here. I'm going to say dot dimensions, but this time I'm going to say triangle instead of rectangle. And I'm going to return S. And in my circle function, make circle, I'm going to have this return type shape. I'm going to declare an instance of shape. Dot dimensions dot circle is equal to circle. And I'm going to return that instance of shape. This okay so far? Yeah.
By doing this, by saying we're going to make a shape instead of just a circle, it should be decreasing the cohesiveness, because now instead of making just a circle, you're making a shape and a circle. Weird question, but
That's a fair question. I think I get what you're asking. So we're doing two things here. We're creating an instance of circle and we're creating an instance of a shape. I think that's what your question is ultimately about. If I'm thinking, is the make circle function cohesive? I'm going to say that yes, it is, because it's stuffing the circle into a shape and it returns that type. If it printed out, this is what the circle looks like while I was creating an instance of the circle, then the function would not be cohesive anymore, because then it's doing two very different things. It's responsible for display and it's responsible for construction. But in this case, I'd say that this is cohesive. This has high cohesion. Yeah.
So as long as like a function kind of like converges to a singular end, makes cohesive. Like even if it does multiple steps, as long as it's doing one like end.
Yeah. So as long as a function is doing a function or a block or a file is doing one kind of end goal thing, then yeah. Distinguishing like what is part of that end goal and what's not part of the end goal, it's usually things like related to display. Displaying something is not really part of the core thing that you're trying to accomplish. It's definitely part of it. You have to display state somewhere, otherwise your program doesn't do anything. But the idea of cohesiveness is really about kind of what you're describing and then separating those things out. Yeah.
returns the items or as cartoon in that environment. So if we make a circle, make triangle, which one actually is going to return back? Or is it that all of them gets returned back?
I'm going to keep going, and I'm going to try to print these things out. And what I'm hoping that we'll see is kind of what's happening underneath when I try to print these things out, okay? Okay. So in my main function now, I'm going to change this. I'm going to delete this triangle line on line 77. And what I'm going to do is I'm going to create a new shape called triangle, and I'm going to make that equal to make triangle of 10 and 50. I'm going to make a new shape. I'm going to call that square, and I'm going to say that this is equal to make rectangle with 10 and 10. I'm going to make an array of shapes, just 5 of them. I'll initialize the whole thing to 0. And what I can say with this array of shapes is I should be able to say shapes at 0 is equal to make circle with a radius of 4. And I should be able to say shapes at 1 is equal to make triangle with a base of 5 and a height of 40. I'm going to compile this to make sure that I'm not completely off base. So I'm going to go to lecture 22. I'm going to add this to my make file. So I'm going to say adding to all shapes. And then I'm going to add shapes to shapes.c. And I am going to also add the complete command here. So clang w all shapes.c minus o shapes.o. And when I clean, I'm going to add shapes. I don't want o shapes.o. I'm just going to say shapes. Okay. So I'm going to quit this. I'm going to make. And I've got a bunch of errors because I'm using uppercase S where I meant to use lowercase s. So I'll fix that. Compile it again. I've got unused variable warnings. And I've got errors related to these semicolons. So I don't want to put semicolons at the end of these. They should be commas or just nothing. So the part that I'm fixing here is in each of the functions, I've got that, that declaration for shape. I don't want to have a semicolon at the end of those lines inside the initializer. Online, I need a semicolon. There we go. And then we've got some unused variables warnings, but that's okay. That's fine. I'm not using those variables right now. Okay, so we have a main function that's able to create different instances of these types that we have, triangle, circle, rectangle, and assign them all to the same supertype, What I'd like to do now is I'd like to go through the process of trying to print out what these things look like. So I'm going to say for int I is equal to 0, I is less than 5, I plus plus. And I want to say printf. And I want to say the shape is and has dimensions, question mark. I want to say that. I do want to say it. But now I have a shape type, and I have no idea what each of those things actually are inside of that array. So here's what I'm going to do. For each of them, I'm going to do this. Printf, if this is a triangle, dimensions are base s d and height d. And I'm going to say shapes at I dot dimensions dot triangle dot base shapes at I dot dimensions dot triangle dot height. Then I'm going to add a line that says printf, if this is a circle, dimensions are base radius %d, shapes at I dot dimensions dot circle dot radius. If this is a rectangle, dimensions are height %d, width %d. And then I do the same exercise here. Shapes at I dot dimensions dot rectangle dot height, shapes at I dot dimensions dot rectangle dot width. I'm going to make this 2 for now because that's all the shapes that I've initialized here. And I'm going to put printf a bunch of equal signs just so we know where the different records are that I'm printing out. And I'm going to compile this, and I'm going to run it. I'm going to comment out these two shapes so we don't get warnings anymore. How long did it take me to type this fast? I say this with total sincerity. When I started, I printed out a cheat sheet for Vim, and I just had it beside me all the time. And I forced myself to remember. And then after a while, I didn't need the cheat sheet anymore. It's just practice. It's just repetition, just forcing myself to repeat over and over again. Okay, so our shapes here were, if this is a triangle, shapes at 0 is a circle with radius 4. So if I've got a circle with radius 4, this is the correct entry here in the middle, radius 4. But what you'll notice is that if I interpret this as a triangle, one of these things happens to be 4. If I interpret this as a rectangle, one of these things happens to be 4. If I look at the structure itself for each of these things, I'm going to go back up to the top of my file. With rectangle, width and height are in that order. I'm going to invert them, and I'm going to make this again, and I'm going to run this again. Now we've got base 4, radius 4, height 4. The other two properties there are 34, but they're just kind of arbitrary values. They are just randomly whatever happens to be in the second 8 bits of that structure. With the second example here, my second shape, if I go back down to my main function, my second shape is a triangle. Both, if this is a triangle and if this is a rectangle, look like they make sense because these are both the same size structures. They both have 8 bits for their first thing and 8 bits for their second thing. A circle has exactly 8 bits, for the one property that it's got. So all of them, for their first 8 bits, happen to show 5 for all of them. Does that answer your question?
It is probably returning this number.
It kind of looks like all of them. It kind of looks like all of them. Dimensions here has 16 total bits. It only has 16 bits. We have 3 things listed in there, and it's 24. Yeah, 24 total bits if we were to add them all together. But this only has 16 bits because it only needs to keep enough space to store rectangle and triangle. Circle just happens to fit in the top 8 bits of that thing. So the structure shape then, when we have an instance of dimensions, this is exactly 16 bits. So this does kind of look like it contains all 3 of these things, but what we're doing here is we're choosing which one it is. And it should be interpreted as just that one type. Yeah. Is it okay with everybody? Any questions so far? This is fine. This is fine, but we're kind of giving the responsibility to the person reading our code right now to answer, did I make a triangle first? Did I make a square first? Did I make a rectangle or a circle first? One of the ways that we're going to solve this is to add a marker to our shape type that says what this thing is. So to my shape type, what I'm going to add is a property that is an array of characters that's called shape type. And I'm going to make this be 10 characters by default. I'm just going to pick some arbitrary size for my array. In each of these functions, I'm going to say that dot shape type, oh, I can't do it that way. I'm going to say it this way. strcpy, this is really, really absurd. I'm doing strcpy. The destination is s.shapetype. The buffer that I want to copy from is the word rectangle. I'm going to have to include string. So I'm going to go to the top. I'm going to go back to make rectangle. And in make triangle, I'm going to do the same thing. strcpy, s.shapetype, triangle. And in circle, I'm going to do the same thing. strcpy, s.shapetype, circle. In my loop, I'm going to be able to ask the question now, what is that property? What's that value in this structure? So what I'm going to be able to say now is if shapes at I dot shape type, and I'm going to use that strcmp function to compare strings. If it's circle, then print out this. Else if strcmp shapes at I dot shape type is rectangle, and I want to say equals 0 for both of these if they are identical, then print out this is a rectangle, so just print out this one. And finally, we only have one other shape right now. This is a triangle. I'm going to recompile this, and I'm going to run it. And now this works. It lets me print out the correct thing for what it is. But this is real tedious. This is really, really tedious to have to do this. To have all of these different properties and all of these different conditional statements that are testing to see whether or not the thing is what I want it to be. The way that we were able to solve this in languages like Java with inheritance and class hierarchies was that we had data in a class, but we also had behavior attached to those classes. My circle class would have a print function or a print method inside of it, and I would just call print on the shape type. My rectangle class would have a print method, and I would just call print on the shape type, and it would figure out polymorphism. It would figure out which method to call in that class hierarchy. So we've got polymorphism kind of sort of. I can assign these different types to each of this one type, but this only gets us so far. We've got polymorphic data, but what I really want is to attach behavior to the data that I've got. The way that I'm going to attach behavior to the data that I've got is to use something called a function pointer. A pointer is a type of variable whose value is an address. The value that we put inside of pointers is an address, and the type, the other part of the type says this is what you'll see when you follow this address, if you choose to follow it this way. Our code exists in memory at an address. I want you to think in your heads about the memory layout, the process's address space. We've got the heap, and we've got the stack, and at the very top, we've got code. Our code it's in memory. It's also in memory. We can point at addresses in memory. If our code exists in memory, then we can also point at code. And we can say that this is something that I want to invoke at runtime. When this is running, I want you to invoke the code that is at this address. Function pointers are variables, and the value that you have for a function pointer is the address of a function. Declaring function pointers is it's kind of messy looking. If I have a function that has been declared to return a character and take a character as input, this is a function prototype. This is stuff that we have seen before. This is a function called func1 that takes as input a single character and returns as output a single character. If I want to make a variable that points at this function, I have to declare it like this. This is a variable that's called pointer fun1. This is the name of the variable here. It is a pointer, so asterisk, to a function with the parenthesis here, and the function takes as input a single character and it returns a single character. That's not too bad. The main thing that we've done here is we put that asterisk in front of it, but this is declaring a variable right now. If I have a function that takes pointers to char and returns a pointer to char, now things are going to start to look a little bit ugly, This is a variable that's called pointer fun2. This is a function pointer with the asterisk. It points at a function with the parenthesis that takes as input a pointer to char, and this function returns a pointer to char. It looks kind of messy. What's the maximum number of pointers you can point to? It's just pointers all the way down. Yeah, it's just pointers all the way down. What I'd like to do is I want to be able to assign things to these function pointers. The way that I assign a value to these, so in the slides that I've got just before this second line here is declaring a variable that's called pointer fun2. To assign a value to pointer fun2, I assign the name of a function without the parenthesis. This is the function that I want to point at with this variable. In that whole end stage process of compilation, these values are populated at that linking stage. So only once we know about all the function implementations that we've got, so we've got all those .o files, only then can we have an address for a function. So these values are populated at the linking stage. When we invoke these function pointers, we use their name and then we put parentheses after it to invoke them. This is the name of a variable, and I'd like to follow it to its address and pass a value to it, and it's going to run code that's going to return something to me. This is a variable, and at its address is a function, and I want to pass to it some data, and when it finishes running, it's going to return something to me. I can invoke them in the same kind of way that I'm invoking functions. Let's add some behavior to shapes. Let's add a little bit of behavior to shapes so that we can get something that looks a little bit more like actual polymorphism. So I'm going to switch back to my terminal. And what I really want to do, the main goal that I've got right now, is I want to have this shape type be able to print itself. I don't want to have to check and see what kind of shape it is in a conditional statement. I just want to say, shape, print yourself out, please. So I'm going to add a function pointer to this. The function pointer is going to be a function that returns nothing. It prints something, so it doesn't return anything. So the return type for the function that I want to point at is void. It is a function pointer, so I have to put this open parenthesis and then a star. And then the name of the value that I want here is print. I want this to be a function pointer that's called print. So in my structure, I've got a function pointer that's called print. What I want print to take as input is an instance of my shape type. I'm going to pass a pointer to a shape type. This declares a variable called print. The type is pointer to function that takes a shape pointer and has no return type. So print is the name of the variable. It's a pointer to a function. The function that it points at must take as input a shape, and it must return nothing. It must have a void return type. Now what I need to do is for each of the types that I want to print, for each of the structures that I've declared, I need to create a print function. So I'm going to start with rectangle here. I'm going to say void print rectangle. It's going to take as input a pointer to a shape that I'm going to call S. And inside of this, I'm going to printf rectangle width %d, height %d. What I'm going to pass to printf to populate that is shape S, and then arrow this time because we have a pointer instead of an actual instance of our structure. S dimensions, that's the name of the union, dot rectangle, that's the type that I'm interpreting this union as, dot width, S dimensions dot rectangle dot height. When I make my rectangle, what I'm going to do is I'm going to assign to my shape type dot print. Remember, print is the name of a variable. The variable's type is pointer to function. The function that it points at must have a void return type, and it accepts as input a shape pointer. Dot print here is equal to print rectangle. I'm going to copy print rectangle so that I can do the same thing for a triangle. Print triangle. This is a triangle with base D and height D. I'm going to change the way that I'm interpreting my union to be triangle. Base and height. And I'm going to add one more function here, void print circle. Shape S. And I'm going to do that last printf. Circle, radius, %d. S dimensions dot circle dot radius. In my triangle function, I'm going to add to my shape type dot print is equal to print triangle. Print is a variable. It's a pointer to a function that has a void return type, and it takes as input a single pointer to shape. I'm going to go to my circle function, make circle. I'm going to say dot print is equal to print circle. Print is a variable. It's the name of a variable in my structure for shape. It takes as an argument, the thing that I want to point at is a function that has no return type, void, and it takes as input a single instance of this shape type. I'm going to go down to my main function now. And I'm going to delete this entire block. I'm going to comment this out. I'm going to leave it here so that we have it for reference. So I've just commented out the entire if-else structure. For me to print this out, what I'm going to do now is in my code here, I'm going to say shapes at I dot print. So I want to call the function that each of these things points at. What I'm going to pass to it is the address of shapes at I. This is the awkward part. A function doesn't have any actual direct attachment to a structure. It doesn't know what owns it or what encloses it. It has no way to go back and say, like, I'm in this class and this class has properties. Functions in C must take input. They must take the input of the thing that they're working with. So shapes at I has a pointer to a function that's called print, but that print function must take an input. If I go back up to each of these print functions that I've declared, they cannot work independently. I can't take nothing here. I can't take nothing here. Print triangle doesn't know about triangles. All it knows is that it can be passed an instance of this shape, and we can trust that it will be passed an instance of triangle because when we initialized a triangle type with make triangle, that's the function that we pass to it, that we put inside of that structure. So I'm going to write this. I'm going to zoom out. I'm going to make this one more time. Int, what I want to do here is I'm going to go down to my shapes at I, and this is what I want. Is that what I want? No, that's not what I want. What do I want here? That's basically what I want. It's going to work the way that I want this to. Where's the error? Oh boy. Unknown type, shape, that's my problem. I'm going to go up to the top here. My problem is that I've done type def of this all at the same time, so I need to say struct shape. I'm going to point specifically at what I'm doing here. The error that I'm getting in this code right now is hidden because I've got a big font size. The error here at the top on line 38 says, error, unknown type name shape. You might have seen something like this if you did something like this. If you did type def struct node and then tried to say node star like this, you might have seen that same error if you tried to do this with your node structure. So I need to change that to be a pointer to the struct shape. I'm going to make this again, and now it compiles. Okay, good. So if I run this one more time, now it's calling each of those functions. So I'll make this a little bigger again. It's calling each of the functions that we've assigned to those types, and it's passing that instance of the shape. Any questions about this? This is a way to use unions, yes. The other place that I've used unions is in file system code, where I'm trying to read a file system. And when you're reading a file system, we've been using the word blocks a lot with zones. Blocks is also a word that gets used with file systems, except in file systems, blocks are all a fixed size. They're all the same size. So with a file system like exFAT, which is what you'd have on a USB stick, each of these blocks are a fixed size of something like, I'm forgetting, I think that a directory entry is 32 bytes. I think that's how big it is. And there are many different kinds of directory entries. So you can have a union of all the different kinds of directory entries And the first bit tells you, or the first byte tells you what kind of directory entry it is, and then you can determine what to do with it after that. So this is a way that you can use unions. There are other ways that you would use unions as well. Yeah. Take operating systems with me, and I will give you an assignment where unions will be useful but not necessary. Useful but not necessary, yeah.
And one question about that, so the way you use that and side effect.
Ampersand or and, I understand what you mean in both cases. So what this is saying is, I'm going to delete these extra parentheses that I added. This was me kind of flailing around, not sure why I'm getting all these warnings. What this says is that shapes is an array, it's an address. At I says, I want to go to the ith element of this array. That's going to be a value. I want to know what the address of the ith element of the shapes array is. That's what this is telling me. We're good. This is going to take a little bit of grokking. Yeah. I would expect you to recognize what a function pointer is. I haven't written any questions about function pointers yet, but this is something that's a learning outcome for the course. Be able to use a function pointer to parameterize behavior. So to be able to pass function pointers around, basically.
Also, the first example, right, you use the string, right?
Yeah.
Initialize the string to whatever it was, and you're writing it in the cell. You allocated that.
So with the structure here, with my shape structure, when I allocate these structures on the stack, the array that's inside them is also on the stack because it's part of that structure. Yeah, so if you did this instead of declaring this as an array, then you could have done malloc to initialize these things. In this case, I was making an arbitrary choice of, I'm going to use that 10 as a maximum value because I know that rectangle is the longest word here and it's not more than 10 characters long. Yeah. I can actually comment this out now. I'm not using shape type anywhere in this code except for the places where I'm copying to it. So I'll comment those out as well. The only other place I was using shape type was in that conditional statement to test to see what kind of shape this was. So the other instances of using that are in there. If I compile this again, it's going to work. And I've accomplished what I think is a better way to do this as opposed to having this giant conditional statement. What this also means now is that as I add new types of shapes to this, I don't have to change the code in my main function anymore. This is a software design principle that's called the open-closed principle. So there's 5 design principles that you'll learn about in Comp 2150 and Comp 3350. So OO and then software engineering. They're called the solid design principles. There's the single responsibility principle, which I've mentioned in class, that is do one thing and do it well. There's the O, which is open-closed principle, and that's this one. It's open for extension, but closed for modification. Now that I can add these print functions to my shape structure, I can just call that print function, and I don't have to keep adding to this conditional statement. Then there's L, which is Liskov's substitution principle. This is named for Barbara Liskov. It's the only one that's named for a person, and it says that I should be able to replace an instance of any type with any of its subtypes, and it should just work. There should be no change of behavior that's defined in the superclass. So if I replace an array list with a hash set, and I call the contains method, it should just work. It shouldn't make a difference which one is actually implementing it. Then there's the interface segregation principle, and then there's the dependency inversion principle. And I'm not going to talk about those because we don't need to talk about that today. Yeah. Okay. If there are no questions about that, I did want to point out this, this library. This is called libcello. This is not installed on Aviary. This is something that you'd have to investigate on your own time. But what you see on the left side of the screen here is C. It's C. This is C. And it's doing things like using the keyword new and types. And it's initializing values and using the var keyword. And it has a for each loop as opposed to making for and while loops. This is cool, but it's a mega abuse of the preprocessor. And I would not recommend using this in a production project, but if you're just goofing off, it might be fun to try using something like this. Heap objects get destructed via garbage collection, it says. This is a library that you include at the top of your file, and it gives you access to this new syntax. It makes it look like something. I don't know what, but it's nicer than working with just base C. I've never used this before, but I see it all the time, and I keep thinking, like, this is cool. There's a table type, and there's arrays, and you can do for each and range. So now it's starting to look more like Python. Yes. And then you can have these points that kind of turn it into a class. Yeah. I'm not saying you should ever use this. I just think it's cool. Yeah. Okay. We got 15 minutes left. So by the end of today's lecture, you should also be able to say that you've seen someone build a crappy C program for the Game Boy Advance. How do you even start with something like this? Okay, to be clear, this is the end of the course. This slide is the end of the course. Yes, yeah. Everybody get out. How do you even start? The first thing you do is you just spend a lot of time reading. I'm going to put these documents up on the course webpage for you alongside this lecture. But this, for example, is a website that's called gbadev.net. And gbadev.net has extensive documentation about the Game Boy Advance. You spend a lot of time reading. You already know how to program. You have to come into this knowing how to program. You have to come into this knowing what you've read, and then a little bit about what people have told you, and then also knowing how to program in a language like C. You also have to spend some time learning about the hardware and its idioms. When we've been doing a bunch of stuff with C, we've been working with Linux, and Linux is a complete operating system. When we're working with the Game Boy Advance, the program that we write is running on the hardware. There is no operating system. It is running just directly on the CPU. There's an entry point, it starts running, and it has no OS. There is no way to clean up your program after it's finished. Your program finishes when the power switch turns off. That's when your program finishes here. Learning about how the hardware is structured and the idioms that it has are part of this. And that's also part of the read a lot about the hardware that you're working with. The other part is setting up your development environment. And this part is what I'm hoping to accomplish with you. Mainly this, get your environment set up so that you can do this, so that you can spend more time reading and figuring out how to work with the hardware that you've got. Game Boy Advance games are not typically written in C. They were not typically written in C. They're not typically written in anything anymore because nobody's making new games for the Game Boy Advance, but they were not typically written in C. They were typically written in ARM7 assembly language. ARM is a kind of processor. M1, M2, all of Apple Silicon is ARM. It's some variant of ARM. Every phone that you have, with some very minor exceptions, is ARM. The very minor exceptions were there were some Intel-based phones a long time ago, but they're not around anymore. Mostly people are writing these games in assembly language as opposed to using higher level languages like C. We're going to be doing this without a library. I'm not using any library code for this. There is no stdio.h for the Game Boy Advance in the thing that we're going to be doing. There are libraries that exist that you can use. This is you reading on your own time after this class. libgba is an example of that. libgba is a library that you can use to work with the Game Boy Advance and the stuff that's fit into that thing. But I'm not going to talk about this because this isn't really related to what I want to accomplish today. Let's learn a little bit about the hardware. The Game Boy Advance was released in 2001, in the time before time, when I was still in high school. It was released in 2001, and it has 2 processors in it. This is a multi-CPU system. It has an ARM7 processor that's running at about 17 megahertz, and it also has a Zilog Z80 processor that's running at either 4.2 megahertz or 8.2 megahertz. So our laptops are running at like gigahertz plus. These are really slow. These are really, really slow compared to what we've got on our desktop machines. Any ideas? Why are there 2 processors in this system? In this case, cohesion is not the answer to this question. Yeah. The Zilog Z80 is there because the Game Boy Advance can also play Game Boy games and Game Boy Color games. It has a complete Game Boy embedded in the hardware of this system. The Game Boy Advance has 96 kilobytes of video RAM, 32 kilobytes of RAM on the CPU, and 256 kilobytes of DRAM. This is off the CPU, so it's physically separated from this thing. My laptop has 24 gigabytes of RAM. Why 24? Because some is attached to the main board and you can't replace it. Yeah, so I think there's 8 gigabytes attached to the main board, and then there's 1 replaceable DIMM. Yeah. So in terms of the amount of memory that the system has, it's a lot smaller. If we go back to the Game Boy has 8 kilobytes of RAM that we can work with. These systems have very little RAM in terms of what we're thinking about in modern day systems. It wasn't even that much for that time. Nintendo has this ability to like reuse and use older hardware because it's cheaper, and then make cool games that are fitting onto that older hardware. The Switch is a good example of that. The processor that's on the Switch is not a new or fast processor, but there are cool games on that system. The games themselves, the cartridges that you plug into the back, have up to 32 megabytes of ROM. So there's memory that's on those cartridges that is up to 32 megabytes in size, but you can't change what's on there. It's just code that you can read and then execute. All that you have for writing is this VRAM, the RAM, and the DRAM. Sometimes there's going to be extra like save spaces for this, for data, but we're gonna think not much about that. It's got a 240 by 160 pixel display, and it does 15-bit color. Remember that each of these are 5 bits in total. I/O on the Game Boy is something that's called memory mapped. What that means is that I can work with the hardware. So the examples that we're going to be looking at are the display, and then input and output, the D-pad that's on there, the buttons that you press. These are memory mapped. That means that in order to get what button is currently pressed, I need to read a specific memory location, a specific address. In order to change what's on the display, I'm going to write to a specific memory address. We can work with bitmaps, and we are going to. Bitmaps here means, well, literally what you think it means with like Microsoft Paint. You pop open Paint, you do some drawing, and you save it as that .bmp file. And what that file format is that each pixel has an RGB value. This is going to be a grid of 240 by 160 pixels that each have an RGB value. It's a bitmap. If you keep going with this, you don't want to do this. You don't want to use it this way. There are hardware support for things like sprites and tiles, and these are hardware accelerated. So when you are doing things like, I want to move the background around really fast, if you do it with tiles, it's going to work a lot better than if you wrote code to update the display to move things around. You do need to know about things like how fast the refresh rate is for the display. You do need to know about things like how to go through different states, but we don't care about that for this setup stuff. We don't care about that at all. We also need to be aware of where in memory our data is going, because some of the data that we have, some of the memory that we have is physically attached to the CPU and some of it is not. The memory that's on the CPU is faster than that's off the CPU, but again, we don't really care for what we're doing right now. Let's start with a simple program that puts some colors on the display. On the course web page, I added the files that I am starting with here. So I've got 2 files that are on the course web page under today's lecture. There's a make file, and there's a file called main.c. I'm going to take a look at main.c right now. I'm going to step through this really quickly. There's stuff here that looks like things that we've done so far. There's stuff here that doesn't look anything like what we've done so far. We have a main function. We have defines, preprocessor directives. We're still writing C. There's a new word that we have not seen before, and that new word is volatile. We've seen unsigned char. We've seen pointers. When we think about unsigned char or char pointers, we're usually thinking, this is a string. I'm assigning to this unsigned char an address. The address that I'm assigning is 4 with 6 zeros behind it. This is a well-known location in memory that lets me do things like configure how the hardware is going to work. I'm picking unsigned char here because I want each entry in this array to be 1 byte. That is why I'm picking unsigned char here. I've added this word volatile because if I make an array in C and I assign values to it, but then I never use those values, I never read them back, my C compiler might say, there's no side effects, so I'm just not going to do that. I'm just going to leave that out. When I generate assembly code, I'm not going to put that in because it doesn't do anything. But in this case, it does do something. This is writing to a register. It's writing to the hardware at a specific location that I would like to use video mode 3. This is an entry in memory, and the value that we're setting here is I want to be in video mode 3. I don't care what that means. It doesn't matter what it means. I'm just configuring the hardware. I want to enable background 2. And the way that I do that is I set the address 0x04000001 to be 0x04. If I don't have the volatile keyword there, the C compiler might say, I'm making these changes, but nothing is used after that, so I'm just going to ignore it. VRAM, this variable, is unsigned short. It's at address 0x06, followed by a bunch of zeros. This is the memory that is used to display stuff on the system. So volatile unsigned short says, I'm going to write to it, and I'm never going to read it. But I don't want you to omit these instructions because they are going to have an effect in the hardware. Unsigned short here says, I want each entry in this array that's called VRAM to be 16 bytes in size. VRAM is pixels. It's the 16-bit pixels that we have, those 15 bits of RGB. VRAM is going to be this massive array that's filled with these pixels. I'm going to do one thing here. And the one thing that I'm going to do is I'm going to say VRAM at screen height divided by 2 times screen width plus 0 is equal to, and I'm going to set this to be 0x001f. This is a red value. That's the last 5 bits of my 16-bit value set. So remember, we have BGR. B has 5 bits, G has 5 bits, R has 5 bits. This sets that pixel to be red. I'm going to copy and paste that, and I'm going to add 5 to this. I'm going to set this to be green. Green is going to be 03E0. That's the middle 5-bit set. And I'm going to do this one more time. Green. And this is going to be 7C00. So this is setting everything in the blue region to 1. After that, I need this program to keep running forever. So I'm just going to say while 1. When the program leaves the main function, it's basically crashing on this system. It's just terminating. So I want it to stay running forever. I don't want it to crash. I'm going to write this. I'm going to zoom out. I'm going to take a look at my makefile. This uses a library that's called DevKit Pro. They have a way to install this on the system, but I would prefer to not install it on my system and instead use something called Docker. Docker is this tool that you can install that will basically let you run commands inside of another environment using virtual machines. These are the commands that will basically take a C program, main.c, and compile it through a .o to something called a .elf. And then it will do .elf to this GBA format using a final command that's called GBA fix. I'm going to make this file, and then I'm going to run it, mgba qt main.gba. And when I said set your expectations to be quite low, this is what I'm talking about. We're putting pixels on the screen. Where's the green one? Oh, you know what? I think I forgot to change. I put them on the same pixel. Thank you. So I'm going to put this one on 10 instead. I'll make it again. And I'll run it. And now we've got 3 pixels there. When I said set your expectations low, I meant set them low. Set them very, very low. If you have followed along to get this environment set up, though, Docker is something great to have on your system in general. This is a tool that you will use in other courses. This is something that you would use in your professional life if you're working in industry. A Game Boy Advance emulator is not something you're going to be using in your industry life. I don't know, maybe you will. Maybe you will, but probably not. So I'm going to put this up on the course webpage. If there's time tomorrow, I'll do something that's a tiny bit more interesting than this, just a tiny bit more interesting. But tomorrow, like I said, what I want to do is spend some time talking about the exam. I want to do some review and then ask questions, have time for questions in general about the assignment and about the final exam. So at this point, you should be able to use function pointers to parameterize behaviors. You should be able to initialize a function pointer. You should be able to assign a function pointer. You should be able to invoke a function pointer. You can also say that you've seen someone build a crappy C program for the Game Boy Advance. That's it. I hope
So you want to go to a real party?
See you all tomorrow.
I figure life's a gift, and I don't intend on wasting it.
Glad to, miss.
Got everything I need right here with me.
Hey, look, 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 look. trying to do the address of the second block
Yeah.
is equal to the address of the first block plus the block size. But that keeps failing. The comparison is
Well,
there another way to compare, or?
Another option might be to do difference instead of addition.
Oh, okay.
And difference will tell you how many spaces are between something. So you could do D2 minus D1 should be equal to block size, I think.
Right,
If
yeah.
that's what you're saying.
Yeah.
But the other thing is that what your code is doing right now is you're not taking the address of, you're not taking the value that's in D1, you're taking the address of the variable D1 itself. And that's on the stack somewhere. If you're doing this comparison, you don't want to put that in front of it.
Okay.
And that will,
Right, because it's already a pointer.
Yes.
It's already pointing
Yeah.
anything.
I'm going to suggest that when you're thinking about this, that the first fit should be, yeah, I think the way you're doing it is right. Yeah. But then, yeah, right now you're comparing addresses
Yeah.
of variables on the stack as opposed to the actual values in the pointer.
Gotcha.
Yeah.
Thank
Okay. Hey,
I just wanted to ask, so like, you said we're already calling malloc like 3 times. So like, how to like assign a size to this? I don't know if this is right.
no. So we don't want to put a block of data inside of our node. There's a pointer to the data region that the zone manages inside of my node, but the data is not inside of my node.
It is not inside your node.
No. So there's a pointer, there is a pointer, and I'm pointing at somewhere in memory,
Oh,
but the thing that I'm pointing at is somewhere inside the data that the zone has inside of it.
okay.
Yeah.
So when I'm meant to put the like data structure in the node, we're just meant to like. When I'm meant to put the data structure in the node, we're just meant to point it at the zone, the data structure in the zone.
Yes.
Oh,
Yeah. Okay. Okay.